Now, we've talked about molecules being achiral in the past, and one of the things to look for we talked about was a plane of symmetry. Molecules that have two or more chiral centers can also be achiral. We warned about this in the last chapter 4 lecture. I warned that while having a chiral center is a good indication that the molecule is chiral, it doesn't always mean that is true. You can have a chiral center or multiple chiral centers, and the molecule can still be achiral. Now, one special version of this is if a molecule is a mesocompound. So, as an example, 2,3-butadiol only has 3 possible stereoisomers, even though it has 2 chirality centers. So you would predict that this would have 4 different stereoisomers. And when a compound has 2 chirality centers and it is achiral, 2 or more chirality centers and it is achiral, we call it a mesocompound. So this is just a special name for a compound that has 2 or more chirality centers. However, it is achiral. 2,3-butadiol has this mesocompound. So it has 3 total stereoisomers. One of them has a RR configuration, and its enantiomer is the SS configuration. These are mirror images of each other, and they are non-superimposable. Now, if we were to write the RS and this would be the SR and the RS version of the molecule, that's what's shown here and here, you would see that these actually end up being superimposable. So even though we have changed the chirality center, this is an S and this is an R, and this one is an R and this is an S, the total molecule ends up being superimposable on each other, making it so that there are not 2 different isomers here, but we just call this one isomer, one achiral isomer that will be called meso 2,3-butadiol. To look for mesocompounds, you want to see if the molecule has a plane of symmetry. Here, this is the plane of symmetry of 2,3-butadiol. You can see that the eclipse conformer, when we move it into its eclipse form, has a plane of symmetry, and the anti-conformer has a center of inversion. These compounds, these mesocompounds, are achiral by definition. So generally, again, you want to look for a plane of symmetry to decide if it is meso. You can always draw out the different isomers as I did here. If any of the isomers, if they're in enantiomeric form, ends up being superimposable, it is, in fact, not chiral, right? Chiral means it has to be a mirror image that is non-superimposable, and thus it must be achiral and a meso compound. So let's do a practice. Here, let's identify molecules that are achiral. First, let's look for chiral centers and then decide if the molecule, because of any planes of symmetry, is ultimately achiral. In our first one, our chiral center is going to be right here. You can see there are 4 different things bonded to it. And this particular molecule and where its chiral center is, it does not have any plane of symmetry, so this is a chiral molecule. Our second molecule has what you would think to be a chiral center here. However, when you look closely, you'll notice that it does not actually have four different things bonded to it. There's a chlorine here, a hydrogen here, but this attachment and this attachment are the same. Notice they're the same length, chain length. There's also a plane of symmetry within this molecule going here. That's a key indicator that this is an achiral molecule. It does not have a chiral center. The next molecule here does have chiral centers, both here and here, so two chiral centers. However, if you were to generate its mirror image, that would look like this. You could see that these would be superimposable on each other. So even though there are two chiral centers in this molecule, the plane of symmetry that exists within this molecule makes it so that it is achiral. Here, again, we have chiral centers here and here. Now, if you generate this mirror image, you'll see that they are not superimposable on each other. That's because one end of this molecule is longer than the other end of this molecule. So if you rotated it around, they would not be superimposable. So these are actually enantiomers of each other, meaning this molecule is chiral. Okay, let's do some more examples. Let's practice drawing stereoisomers and figuring out whether they are enantiomers or diastereomers, or if they have a meso compound. Here's our starting molecule, and let's think about possible stereoisomers that could exist for this molecule. First, let's identify where it has chiral centers. This particular molecule has two chiral centers, one here and one here. So I like to draw out the version of this molecule that's going to help me identify the R and S configurations. And the easiest way to do this for me is when I know that there's a hydrogen, for example, at this chiral center, there's a hydrogen here and a hydrogen here. I'm going to draw the first version where my hydrogens are in the back. That's going to help me assign my R and S configuration very easily. So let's assign the RS configuration to this chiral center with the OH. Here, the OH, the oxygen is going to get precedence as 1. This would be 2, and this would be 3. So this is going clockwise, making this an R configuration. At this carbon, the bromine gets precedence. So this is 1, this would be 2, and this would be 3. So again, this now is going still clockwise. So this is also our configuration. So let me just draw that out again. Okay, so this version would be R, R. Now you can imagine if I took the mirror image of this, if I flipped it, meaning the OH is in the back here, and the OH is in the back, or the BR is in the back here. This would be the S configuration. Now, we also know that we could have a version where we have combinations of R and S. So this would be the R S configuration here. And here we could have the S R configuration. Now, how are these related to each other? This RR configuration and this SS configuration, when we generated them, I already said, here's the mirror image. So these are enantiomers of each other. Similarly, if you look at these two molecules, this RS and SR are mirror images of each other, so they are also enantiomers. The rest of the relationships between molecules should then be diastereomers. This is a diastereomer of this one and this of this. Similarly, across is also diastereomers. So here are all four of our possible stereoisomers, and we've drawn out the four different combinations, and we've shown which ones are enantiomers of each other and which ones are diastereomers of each other. Now here you'll notice that this molecule does not have any plane of symmetry, so there are no meso compounds. Okay, let's try another one. Here's a different molecule. Again, we want to identify all the possible stereoisomers for the following molecule and indicate the relationship. So again, first, let's find where the chiral centers are. Here and here are carbons with chiral centers. So I'm yet again going to draw my chiral centers so that I have the hydrogen pointing back as my first version. And I'm going to assign the R and S configuration to that version first and then work from there. So in this version, I'm going to have both of my OHs pointing outward and my hydrogen will be in the back. Okay, so here, let's assign priorities. Attached to this carbon is an oxygen, and then here is a carbon, and here is a carbon. This carbon has a double bond to an oxygen and a single bond to an oxygen. And this carbon has a single bond to an oxygen and a single bond to a carbon. So the priorities here would be 1, 2, 3. So it would go this way, which is counterclockwise, so this would be S. And our other carbon, it's kind of in the opposite position, so its priorities would be here, here, and here, 1, 2, 3. It's going to be going this way, which is clockwise, so this is R. I'll redraw that. And show its assignments here. Okay, so this is a S and this is an R. Now let's think about the mirror image of this molecule. Now if we just flip both of those, it should look like this. This will be going back and going back. And this would be R, and this would be S. Okay, let's think about other generated combinations. So we could have one going forward and one going back. So this one going forward is S configuration, and this one going back is also S configuration. And then the last version we could have is if we have one going back and one going forward. And this would be RR configuration. Now, normally we would look at all of these and see their mirror images. So these are mirror images, and these are mirror images. So you would innately say this is an enantiomer and this is an enantiomer. However, if we look at this mirror image and this mirror image, and you flip this compound around, you notice that they actually are superimposable on each other. So these two are a mesa compound. They're the same, and they are achiral. So this is the same version, this molecule is the same version of itself. And that again is because when we look at this starting drawing, you can see that there is a plane of symmetry that exists in the molecule. So these two are non-superimposable at the bottom. These are enantiomers, they're non-superimposable. However, these two we're just going to call one compound. It is the meso compound. And it is related to the enantiomers as a diastereomer. That's how it is related. So we have these two, which are enantiomer versions of themselves. And then they are related to one meso compound. We call this one compound. And they are diastereomers to this. So this molecule only has 3 isomers. It has the SS configuration, the RR configuration, and the meso configuration.